Okay, this video is kind of just a general overview of some different topics when dealing with derivatives. So the first part is just notation. Just know that all of these things mean the same thing. So a lot of times you're going to see something and you're going to think of, I've never seen that before, or what does that mean? And all of these things mean the same thing. The two most common ones that we'll look at are probably f prime of x. Okay, that means the derivative of a function whose variable is x, whose independent variable is x, right? F prime of x, y prime, dy over dx. So that means basically think of it as the change in y over change in x, right? So it's like a slope. That's what we think about when we do derivative. We think about the slope of the tangent line. So dy over dx is what we're looking at there. Df over dx, again just replacing y with f there. Sometimes you'll see this d dx of f of x. I'll use that notation when I give you a function f of x and I want you to find the derivative. I'll just say like do d over dx of f of x, and that just means take the derivative of f of x. Okay, so you'll see that sometimes. And then sometimes you'll just see them replace all of that with a capital D. D f of x means the derivative of f of x. And then this last one is a little subscript of x. That would tell us that make sure you do the derivative with respect to x, is what that's saying. That's something that we'll talk about much later on down the road. But what I want you to know is that notation-wise, all of this stuff simply means find the derivative of the function that you are given. Okay, so all of those things mean the same thing. Next up, we have a theorem. It says if f is differentiable at a, so differentiable in itself means that a function, you can find the derivative of the function at some x value a. And sometimes you have situations where you can't find the derivative at an a coordinate. An x coordinate that we'll call a. So differentiable just means that you can take the derivative at that x value. So if f is differentiable at a, if I can take the derivative there, then f had to have been continuous at a. So that means that, if I know it's differentiable there, then I know the function was continuous. However, the converse is false. So what that means is I can't flip differentiable and continuous and make this make sense. It is not guaranteed that if a function is continuous at a, that it's necessarily differentiable. So in this illustration below, I'm showing you an example of how we can have a continuous function that is not differentiable. And what you really want to look out for is what we call cusps. So this is what you call a cusp. And a cusp is where a graph comes to a sharp point. It's continuous through there. The graph continues. I go up, I hit this sharp point and continue on. It's continuous at A. I don't have to like pick my pencil up and I don't have a jump or a hole or an asymptote or anything like that. It is continuous there, but it's not differentiable there because what you could have happen here is you could have a tangent line through that point right there. Like your tangent line could go straight across. Your tangent line could go like this. It could go like this. The idea is there are a lot of different lines that I could make that only hit that one point on the graph there. And therefore I don't get a unique tangent line through that, which means it's not differentiable there. So watch out for cusps. If you have a cusp, it is continuous there, but it would not be differentiable there. I can't find the derivative of a at that point there. Another situation would be if I have a tangent line that is vertical through a certain point. So if this point right here gave me a tangent line that would be vertical, remember a vertical line is an undefined slope, and so therefore that's another situation where it's not going to be differentiable even though my graph was continuous through that point. Okay. So a couple things to watch out for there. Next up is higher derivatives. This is something that we will do a lot of, and it's simply to find higher order derivatives. So if I have the first derivative, well, how can I find what's called the second derivative? So the second derivative just looks like this. I have two little prime marks there. F double prime is what I'll call that. F double prime of x, that means the second derivative of f, or the third derivative. And then typically after 3, you'll just see like a number there, meaning find the fourth derivative and the fifth derivative and so forth. And they'll stop making little hash marks after 3. But there are real life situations where we need to know second and third derivatives, and so we're going to need to find those algebraically. In a previous video, so the directions here are to find the second, third, and fourth derivatives of this function. In a previous video, I found the first derivative of this. So f prime of x, we found this in a previous video, was 3x squared minus 1. So if I want to find the second derivative, f double prime of x, what I want to do here is the limit as h approaches 0 of f of x plus h, so that's going to be 3 times x plus h squared minus 1, minus f of x, which would be 3x squared minus 1, all over h. Now, I'm saying f of x, I should be saying this. F double prime, when you go to use your limit as h approaches 0 function, sorry, I should have said this before, you use the previous derivative. So I don't go back to the original function, right? So my first function was x cubed minus x. The derivative of that was 3x squared minus 1. I want to find the derivative of that. So to find f double prime, I'm replacing, I guess in my definition, f of x plus h with f prime of x plus h minus f prime of x. I'm just taking the previous derivative and plugging that in for my derivative function here. And I'm going to simplify this and cancel some things out and get a function. So that gives us the limit as h approaches 0 of 3 times, if I do x plus h squared, that's x squared plus 2xh plus h squared minus 1, and I'm going to go ahead and distribute my negative here, which would be minus 3x squared plus 1 all over h, which gives us the limit as h approaches 0 of 3x squared plus 6xh plus 3h squared minus 1 minus 3x squared plus 1 all over h. Now I can go through and cancel some stuff. 3x squared minus 3x squared and minus 1 and plus 1. Those will all cancel. I can then cancel an h from each of those terms with the h on the bottom, which means we have the limit as h approaches 0 of 6x plus 3h over 1. I'm sorry, so I don't really need to worry about that. And I can evaluate by plugging in 0 for h, which means I just end up with 6x. So f double prime, my second derivative of x, is just 6x. Now I'm going to go ahead and evaluate these other ones. I promise they'll take less time because my function is starting to become smaller and smaller here. So the third derivative of x is the limit as h approaches 0 of, and now I'm going to use f double prime, so I'm going to use this I just found. So I'm going to do that evaluated at x plus h, right? So f of x plus h minus f of x, which is just 6x all over h. And again, we get something that's going to simplify really nicely here. Limit as h approaches 0 of 6x plus 6h minus 6x all over h. Your 6x and minus 6x will cancel. Your h's cancel. You just have 6. So when you evaluate the limit, plug in 0 for h, well, there's nothing to plug in 0 for, so I just am going to end up with 6. So that's my third derivative. It's just 6. So track it here. So our original function, x cubed minus x. First derivative, 3x squared minus 1. Second derivative is 6x. The third derivative is just 6. And now I am going to go ahead and find the fourth derivative. And you may wonder how I'm going to do this because my third derivative is just a constant here. But if I do limit as h approaches 0 of f of x plus h, well, replace all the x's in this function with x plus h. Well, I still just get 6 because there's nothing to plug in there. So I get f of x plus h minus f of x all over h. Well, what happens there is I get 6 minus 6 over h, which is 0 over h. Now, I can say here 0h over h and cancel those out. I'm going to end up with 0 here. And that's going to lead us to this idea, which we'll talk about in a later video, about what happens when you do a derivative of a constant. You're going to end up with 0. Okay, so notice how that function got smaller and simpler as we went along there, finding each one of those derivatives. So higher derivatives is important. We're going to need to know to do that. You just keep taking the derivative of the previous one to get your next derivative down.